Welcome to What's New in Energy Minerals. I'm so glad you could join us this afternoon and hope that you enjoyed the excellent presentations and the conference so far. I've had a great experience so far, very well organized. I mean, there are a few mishaps, but that was to be expected. But overall, it's been just a great conference. And I hope you checked out all of the different sessions on energy minerals, alternative energies, and sustainability. Today, I wanted to present to you and highlight some of the amazing work that our committee members are doing in Energy Minerals Division. We have about 9 committees and actually about to get a 10th. We have bitumen, heavy oil, coal, coal bed methane, critical minerals, energy economics and technology, gas hydrates, geothermal energy, tight oil and gas, uranium, and are in the process of establishing a helium committee. So some of us will share our results from the last year in a brief talk, followed by question and answers. We have these experts are writing reports every year that they've either published in Discovery or Search and Discovery. We've also had publications at the National Research Council that Fran Hein edited a few years back. And all these reports are published on the EMD website. And some of them are 300 pages long. So very informative, very detailed, some of them. And I really encourage you to check those out if you wanted to learn more about some of the Energy Minerals Division work. So today, I'm going to share my screen here. We have 6 of our committee members will be, I hope you can see this little spreadsheet right here. 6 of our committee members will be talking about the different work they've been doing. And we're going to start with myself. I used to be the chair of the tight oil and gas committee, but now Justin Birdwell and Lucy Coe have taken over since I'm president this year. This is being followed by Michael Campbell, who is the committee chair of the uranium committee, and he will be talking about some of the critical commodities that he's chairing and an expert on, for example, the uranium, thorium, helium-3 rare earths. Then Dan McConnell will be talking about gas hydride production testing. He and Tim Collett are the chairs of the gas hydride committee. Ian Kirkland then will talk about dynamic changes in heavy oil imports to the US Gulf Coast. He is the chair of the bitumen and heavy oil committee. Jack Pashin will give an excellent talk about developments in coal bed methane. He's the chair of the coal bed methane committee. And last but not least, Jeremy Platt and Dieter Beike will be giving us an update on the energy economics findings for the last year and for 2020. So the format will be as planned. There's 10 minutes of talk, and then hopefully we have 5 minutes of question and answers. I encourage you to type your questions into the format window, into your window, question answer window, and I or Jeremy Platt will read those out to the speaker. So now I will be sharing another share. I will be starting with the our presentation for the energy minerals, I'm sorry, for the tight oil and gas committee activities that have been going on this year and last year. And my co-authors that have been taking over basically are Lucy Coe and Justin Birdwell. I wanted to very quickly give you a brief overview of the committee. It started about 15 years ago, basically with the onset of the shale revolution. And Neil Fishman, he was instrumental in establishing and guiding this committee. It first started out with reports on US shale gas, and then basically moved over to US and international shale oil and gas fields. And usually the report contains highlights of US and international developments in the shale, in the tight shale oil and gas plays. Yeah, last year we decided, because not too much activity in tight gas sands and there was just too much fragment, we decided to merge the tight gas committee with the shale oil and gas folks, and now reporting on all of the tight formations, whether it's shale, sandstone, or carbonates. We usually disseminate technical information on the largest developing place in the US and the international basin. And the reports are published either, as I said before, in Search and Discovery or on the EMD website. So I'm handing over to Justin, and he will show you some of the updates in the US, and Lucy will show you the updates in the international realm. Justin?
Thanks, Ursula. So as Ursula mentioned, we're now the Tight Oil and Gas Committee, and that's made up of a couple of different tiers of folks. We have our committee leadership, and I'm the current chair. Lucy Coe has been my co-chair this year, and Wayne Camp is our vice chair representing industry. We have two new vice chairs coming on, I guess technically this month, and I'll be stepping down as chair, and Lucy will be chairperson going forward. So that's one tier. We also have an advisory group of experts that are listed on our webpage, who we consult with on issues related to tight oil and gas, and who also contribute in some cases to our commodity reports. And then we have contributors who typically address one or more major basins in the US and internationally. A couple highlights from this year. Recently, several current and former EMD participants published memoir 120 from AAPG that has information on petrographic and different microscopy methods as they apply to mudstones. We have added some new components to our commodity reports. We'll now be including background documents that have a summary of important play properties, and that was something that Wayne Camp had recommended. And you can see a small example here. I'll have a slide with a little more information coming up. We've also updated our web page to better mesh with the updated AAPG web presence. It includes some new resources, links, and we're hoping to add some additional information and get some of the current outdated material updated very soon. We've recruited some new contributors, and I'll talk a little more about that on the next slide. And we've increased and plan to continue increasing our focus on applications or facets of utilizing oil and gas technology for other sorts of resource recovery, like looking at geothermal from either dry holes, shut-in holes, or as a co-product in producing holes, looking at brine resources similar to lithium and bromine mining from the Smackover in Arkansas. And then there's some new ideas around how to potentially recover hydrogen from heavy oil reservoirs. And so these are things we're kind of keeping an eye on and deciding how to maybe incorporate those into our work for the committee. Here you can see a list of the current committee contributors. These are the folks who actually submit reports every year on what's new in the particular basin or state or region that they've agreed to report on. You can see we're a little short on international contributors, and we have a running list of formations we would like to potentially address. Not all of these maybe would be included, but just some of the ideas of things that we aren't currently covering that we would like new contributors for. So if you have any interest, please reach out and let us know. This, again, just a quick review of one of the new components of our commodity reports. These are place summaries. Again, this was an idea that Wayne Camp had come up with, and he generated one of the first examples for the Barnett. And we were all like, this is great. We're going to do this for all the other formations. And so here's my incomplete first crack at the Eagle Ford. I've since updated it, and it's got a little more, few more of these blanks have been filled in, but they contain, in addition to these just tables of information, we've included stratigraphic columns, type logs, maps of important geographic features, and then usually a short commentary describing the formation and some key references for recent papers and maybe classic papers on those systems. So that's what the EMD Title and Gas Committee has been up to this year. Obviously, the unfortunate headline for 2019 and 2020 has been that things are tough. And I won't go into a lot of detail on this slide, but you add it all up, and since the onset of the COVID-related economic disruptions that we're all enjoying, there's been about a 2 million barrel per day drop-off in production from tight oil formations, according to EIA, or the U.S. Energy Information Agency and or Administration. And gas, it hasn't been quite as bad a drop in some formations, but oil has really been hit pretty hard by the lack of demand and the decrease in drilling. So there's hopefully a big recovery coming, but for now it's looking a little better in some areas, but not great everywhere. So with a little more hopefully good news, I'm going to hand off to Lucy so she can tell you about the international developments.
Thank you, Justin and Ursula, on the great introductions on the U.S. conditions and then the Thai Oil and Gas Committee in the Energy and Mineral Divisions. I'm going to cover what's happening internationally on the Thai oil and gas resources. As you see earlier on Justin's introduction, we are currently recruiting experts who knew or have experience operating in these areas, basins or shales. And we welcome you to join our EMD committee, Thai Oil and Gas Committee, I mean. So I will give you some brief introduction that we know of in Canada, China, Europe, and South America. And just on the bottom right-hand corner, this is a rig count. I mean, that not limited to Thai oil and gas resources, but as Justin said, they're significantly impacted on the drilling activities, not just in the US, but also internationally. And so Canada has been developing Thai gas production and resources, I think, since 2005. Their first horizontal drilling and multi-stage fracking came from Montney Formation in British Columbia. And since then, the other big resources plays are like Horn River Basin, Liar Basin, Montney, Duvernay, and the Bakken equivalent, which is the actual formation. So these are quite actively being drilled in Canada. And you can, on the left-hand side, the graph here, you can see where the production moves in the Montney play. And that sort of correspond to, different products like oil or dry gas or condensates. Canada actually have a lot of open resources online. So if you go to the website that I show you here, you can see a lot of detailed information. So this is just an example of their active rigs right now in terms of areas where they have active drilling rigs in terms of oil and gas wells or total wells versus currently drilling wells. So right now, this is the data from September 29th, and you can see data from a year ago. So right now, currently the most activity is still in Alberta and then British Columbia and a few in Saskatchewan. And so they have 32 gas wells right now and 24 oil wells. What happened in China is quite different. So China is still really active even during this COVID time, just because they really need they really consume a lot of natural gases and they aim to boost their domestic gas supplies. And marine shale, although China has a lot of lacustrine basin, that's like what you see here, Tarim Basin, Yongar, Ordos, these are all big lacustrine basin. But one of the most successful basins that's been developed is in Sichuan Basin. It's a marine shale gas place. So their exploration starts in 2006, and they have kind of three stages. So 2006 to 2020, it's their investigation stage and evaluation. And in 2020, they have some major breakthrough in marine shale gas exploration. And they found their first shale gas field, Fuling gas field in Sichuan Basin. And since then, a lot of activities has been developed. Other formations like Wufeng Formation and Loma C Formation, both in Sichuan Basin, have been heavily explored. And right now, they think they are enter a golden age of rapid progress of exploration and development. So this is what happened in China. And in Europe has a lot of shale basins, but has very limited activities due to their, in general, public concerns about environment, hydraulic fracturing impact, and climate footprint. So Poland was once quite active, but it's no longer anymore. So far, fracking is most actively in UK, but then they are very heavily regulated as well. So, and the first UK shale gas well is drilled in 2010 in the Boulder Basin. And then EU in general has a lot of regulation monitoring programs. So you can go to their website, M4 Shale Gas. This is part of their 2020 research and innovation program. And currently, even there's not a lot of activities in Europe. There's still ongoing research going on. So geological surveys, such in Denmark, Germany, Netherlands, or UK, they're still doing evaluation, especially for the offshore unconventional resources. So the offshore equivalent of their onshore unconventional resources. So last is the South America. South America has also a lot of resources, and the most famous one will be the Vaca Muerta in Neuquén Basin in Argentina. And there's some political change in Argentina currently with their change in state secretary, in energy secretary, and who used to work actually in YPF. And the Vaca Muerta development has been impacted by the COVID as well, and has the production has been decreases as well. But I heard that things are to start picking up, especially by YPF. And Brazil is also planning to drill their first pilot shale drilling project in the Paraíba Basin. And this is just an example of who are in the Vaca Muerta. They also attract a lot of international oil and gas companies as well, like Chevron, like Exxon, like Total, like Dow Chemical, and YPF and Techpetrol are their local state oil and gas drillers. So this is what we have for the first session on the Thai Oil and Gas Committee, and we welcome you to join us. And if you have any questions, please let us know. And I know my time is up, so we might need to move on to the next talk.
One quick question, Lucy. Has there been any development of tight gas sands in the Dutch sector of the North Sea?
in the Dutch sector of the North Sea?
Yes.
That I don't know. I'm not aware of that. Do you know any?
I think
I didn't see any.
there has been before. I mean, historically, I think historically the Shell has been developing some of the Rotliegende, some of the tight gas sands, but I'm not 100% sure if they've used some of the unconventional methods.
Oh, I see. I haven't seen any like recent news about that, but we can pay attention to that and just.
There's an article from July of this year talking about tulip oil pulling out. So the price point being what it is, it was something that was being considered, but it's been sort of shelved for now.
Yeah.
And Groningen too is on a path to shut down.
Mm-hmm. Excellent. Let's move on. We are running a little bit out of time. Thank you, Eric, for your comment. Appreciate it. We'll have Michael Campbell now share the screen and tell us all about the uranium.
Here we are inside the Uranium Committee, and I want to briefly indicate what the real role of the UCOM is all about. And that is to advise the membership of the AAPG and the general public on what uranium is doing, what nuclear power is doing, because let's face it, they're in competition. We do, as Ursula mentioned, we do an annual report, and our chair and our committee, you can see right here, and I won't spend any time on that, but what's going on in nuclear power? Is it going to have a greater role in energy today and tomorrow? The answer, as far as we can see, after spending years of monitoring what's going on, is that certainly right now it already contributes a lot of power to the U.S. and around the world. And this whole program or this whole presentation will be released on YouTube here shortly, so that you can go back and look at what's going on. But I would also urge you to download the PDF version so that you can take advantage of the links we have included here. If you notice, everything in blue here is actually a link. So let me go first through what nuclear power and where it is right now. There's a big move on. But it's trying to get over some of the past problems. Yes, there were problems. Yes, there were incidents, 3 Mile Island, then Chernobyl, and then Fukushima. However, the thing to remember is no one died at 3 Mile Island. No one died at Fukushima in the plant area, at least. Chernobyl was an entirely different thing. That was a Soviet era design problem that the West had been warning about for years. So we don't count that. Yes, a lot of 25 or 30 people died and children got thyroid. But all in all, over the years, the nuclear power industry has learned to handle these problems. And I think it's going to be put everything behind them and move forward. The safety record, when you look at the past 40 years of nuclear power operation, it has been better than coal operation, better than oil and gas. And so that is not a problem. Does it compete with oil and gas? Yes, indeed. When you're looking for the fuel, uranium is only about 5% of the actual cost. And is nuclear power climate friendly? It certainly is, but it's also business friendly. This area on the right here you see is for you to read later. It's a little synopsis we put together for your consideration. Okay, one of the problems we've always had is what about the waste? Well, it turns out that only about 2,000 metric tons of used fuel is generated every year. And if you take all the waste that have ever been produced since the 1950s, it's about 83,000 metric tons. You could fit all that in a football field size and about 30 feet deep, and that's it. The trouble is the federal government did not come through years ago as required by law to build a storage facility such as Yucca Mountain, but that has didn't pass the geological tests apparently. But we still have the WIP project down here in New Mexico, and that's storing high level radioactivity. But so the waste is sitting now mostly on the nuclear power sites, and you can see on the right here in these casts, they sit there quite well. There's never been a problem in leakage. Now, what are we looking at in terms of the number of nuclear power plants in the world? There's 441 operational reactors in the world. There's 57 plants and 95 reactors in the US in 29 states. And that's about 68 million pounds of fuel that's needed to fuel those plants. So it's quite an activity. Are we going to be able to build enough of them? We'll see. There's 54 reactors under construction in the world these days. Only 2 of them are being finalized and constructed in the U.S. here today in what is it, Georgia and South Carolina. We monitor what's going on between the wind and solar, as well as oil and gas as it impacts what nuclear power is doing. And we realized over the years that the US EIA has been reporting a lot more actively about renewables than they do about nuclear power. I raised Cain about that a few years ago with the people in the EIA, and all of a sudden the next year they start putting out all sorts of extra coverage in nuclear power, and have been doing so ever since. Okay, one of the things that I want to bring to your attention here, and I forgot to turn on my clock, but anyway, the wind and solar energy group people are actively in need of a backup power grid. Now, in California, for example, since they decided to back out of most of their nuclear power plants, they're using natural gas. So is Germany and a few others. But the price of electricity is going out of sight, and we think that that's going to be a dominant player in the future. All right, what's coming down the pike? Something called small modular reactors, or SMERs. These are small nuclear power plants. They can be, they're unitized. You can decide how much power you actually need. We'll have them probably in the next 10 years. And they're reasonable operating costs and minimal waste handling. And I think that's actually going to come on rather quickly. Now, where is the uranium coming from? Over the years, it's come from Uzbekistan, Kazakhstan, Russia, Australia, and Canada. Some of those are let's say politely, rather insecure sources. And so the uranium industry in the past few years in the US has asked the federal government to give them some protection. And there's plans like that to develop a uranium reserve, not unlike the Strategic Petroleum Reserve of many years ago. And we'll see how far that goes. You'll notice in some of these areas where you see history alongside of some of the bullet points here, that gives you an opportunity to get into the database of the I2M web portal that will give you the list of chronological list of papers and reports and what have you on that particular subject. Now, uranium is explored by small rigs. Those are, in many respects, water well rigs, 500, 600, 700 feet. But in some of the uranium ore bodies are now down 1,200 feet. You can see the sediments that come up for geologists to look at. And you can see the various sample shading and various oxidation levels that gives you a clue as to where you're going. In South Texas here, you'll see one of the companies has a central processing plant, and they use the in-situ mining approach to bring in pregnant solution to the central processing plant. Down here to the south, as you can see, down in Altamega, a project I worked on a few years ago, that is typical for that area, and we have no doubt that it trends into that trend goes into Mexico, as well as the trend goes up to in north of Goliad and not too far from Houston. We've listed down here where uranium occurs. For example, in this picture, you see something called Coles Hill. That is a major uranium discovery. Hasn't been mined. The locals decided they didn't want uranium mining in their area, but that's a world-class uranium deposit. And one of these days that will be developed, I have no doubt. There's a whole trend in South Texas. This trend comes up into East Texas, I have no doubt. And you can see some of the other areas. In addition to Alaska, the Bocam Mountains, a major uranium and rare earth deposit, as well as a project we've been working on in the Seward Peninsula that not only has very, very high grade uranium, but also rare earths. Yeah, let's go on to what it really looks like. Most of the uranium in the U.S. is in a form called roll fronts. This you can see here that is rolls around in a geochemical cell as it moves down the dip. And this is surrounded by other types of mineralization, such as selenium and molybdenum, which is usually put in a waste stream after the processing, or can be sold off as a subproduct. Other types of uranium are in something called carbonatite groups and porphyrin igneous rocks, and those make up most of the others. Of course, one of the biggest ones I've got to mention is the unconformity related uranium that occurs in Canada. Canada has huge amounts of uranium. We're in the Athabasca Basin, around the edge mostly, and most of these grades, especially as you get deeper, you get close to stoichiometric in that you're looking at 25, 26, 28% uranium, which is so high that in some of these underground mines, they're going to have to use artificial intelligence and remote mining because that would create the radon and the radium coming off of that kind of uranium deposit would not be all that healthy for the miners.
1 minute.
Yes, 1 minute. Okay. This is an exploration guide that Associate of Mine put together in the 70s to help guide the exploration drilling. You can see these black things are drill holes. And we use the geophysical logs as well as the geologic logs to help tell us where most of the ore is. And yeah, if I'd remembered there, where most of the ore is, and that goes a long way. Okay. All right, pricing. Just a couple minutes. The uranium industry has gone through a lot of fluctuations.
We have to get to the next speaker.
Okay. How many minutes do I have? Okay. Let me close by saying, take a look at this material here, especially with respect to Russia and opposition media groups. So the prices come back, and we think it's going to continue. So on that, I will close and let you read that when you get the PDF and the presentation that will be available on YouTube shortly. Thank you.
Thank you so much, Michael. Great talk. And we're going to, don't have any time for questions right now. And Dan McConnell will take it away by sharing his screen. Michael, please unshare your screen.
Great.
Thank you.
Yeah.
Okay, well, Tim Collett asked me to give a talk. I said it's going to be a TED talk on gas hydrates. And will gas hydrates contribute to the energy mix in the future, and when? And gas hydrates tell a fascinating story. So let's start with one. Bill Walton's my brother-in-law's dad, and Bill's career was as a logging engineer for Dresser Industries for about 30 years. He comes over on Thanksgiving, and every Thanksgiving, he tells me the same story, and it goes like this. It says, he would be logging, coming up from logging a section, and they would pass through some thick shales with hydrocarbon, and he would dutifully report the results. He would say, there sure is a whole lot of hydrocarbon in this system, in this section, in which the well site geologist would say, forget it, it's in a shale, you'll never get that out. So forget it. Forget it. It's in a shale. You'll never get that out. And that's what they say about methane hydrates. Well, that they're methane hydrates and we won't get them out. So there's hundreds of thousands of TCF in natural gas hydrates that may be out there, and we'll never get those out. Well, for shale gas, we know how that turned out. So at the top, you see hundreds of thousands of TCF of Arctic sands. We have marine sands that tens of thousands of TCF, but most of it is in muds and fractures. So will gas hydrates ever be a resource? Well, can they be produced? We think so, but there are challenges. So what are hydrates? They're naturally occurring solid form of hydrocarbon composed of light gases and water. And that's it, really, natural gas and water. Some people call gas hydrates nature's LNG because it's a relatively dense energy source. 1 cubic meter of methane hydrate is equal to 164 cubic meters of natural gas at STP, plus a lot of water. So if natural gas is at the bubble point in the sediments and it's cold enough, like in the Arctic or under pressure beneath 500 meters or more of water, there can be gas hydrates there too. And in the petroleum systems handbooks that we have, when they mention gas hydrates, they just mention them as indicators of a petroleum system. But if they really are such a large part of the petroleum system, wouldn't we know about them already? And wouldn't we already be exploiting them? So natural gas hydrates are common at seeps, of course. So we see those, and that's the top of the stability field. And they were and then the base of the gas hydrate stability field was discovered as a really strange reflector that consistently offset the seabed, but in cross-cut stratigraphy. And it was this discovery that set off the imagination that the resource really could be huge, because there's huge parts of the planet that are cold enough or under enough hydrostatic pressure where you could have host gas hydrate. And then large areas of BSRs began to be documented. So if they're everywhere, why aren't they on the radar of oil and gas companies? We're here at the AAPG. Well, they have been on and off, but most recently when it was thought there would be supply security for natural gas. Countries without an endowment, or like Japan, researchers were really excited to see bottom simulating reflectors around the islands on the east coast of Japan, and they launched government research that's carried out at that time. And at that same time, here in the United States, we had the Methane Hydrate Development Act of 2000 here in the U.S. So there's other countries, China, India, Korea, and others, have all been active with methane hydrate laboratories and field programs. So why is there such a disconnect with the oil and gas industry? If they're something that's supposed to be everywhere, gas hydrates really have not been everywhere. And in the Gulf of Mexico, where deep water oil and gas development first started, over a leaky hydrocarbon system, nevertheless, hundreds of exploration and production wells were drilled, with little or no indications that anyone ever penetrated any gas hydrate. And that was a mystery. It was a puzzling. And for one, nobody could find any bottom simulating reflectors either. So my own start with gas hydrates started as a geohazards interpreter. And that was something on the shelf, was something that you would do in order to avoid unseen gas pockets. But when we got to deep water, it really changed into just better top hole drilling guidance in deep water settings. But it was still a mystery. We knew that gas hydrates were on the seafloor, but the commonly accepted base of hydrate stability was absent. But that paradox actually led us to some discoveries, because now we can find high saturation gas hydrate sands and drill them probably with a much greater success ratio than we could for conventional deep water oil and gas prospects. my first insight for gas hydrates was at Green Canyon 955, which is shown here. And I was just mapping out the top of topmost gassy sediments, and I did not understand why the gas was not moving up faults into a channel levee system that was there. And so I postulated to my client that it was the gas hydrates were the control. The other insight that came a little bit later was that there would be a specific seismic attribute that would tell me that I had a hydrate-filled sand. And so is this little one right here. And it was in this thinking, gas hydrates would not have some sort of uniform distribution from the seafloor to the base of hydrate stability. They would tend to be patchy accumulations where gas flux either from focused biogenic gas or mixed biogenic and thermogenic gas accumulated. And then later in 2009 with Chevron and the Department of Energy, we drilled on that attribute, that little attribute that I just shown you there. And it was really just a hard streak in a sand, but we had a pre-drill prediction of what the saturation of gas hydrate would be from that. And the second insight, and it turned out to be true, and there was a session this morning about that hydrate. In fact, the whole AAPG September edition is all about these gas hydrates, actually. And this, the second insight that I had was at Walker Ridge 313, and this is where we had a pattern of gassy sediments and steeply dipping sediments. It was easiest really to explain as being the base of hydrate stability, or a connect the dots BSR. And a seismic inversion, which I'm not showing you here, showed that we could expect a specific attribute for hydrate fill. And this section here that's boxed out, that's fully saturated gas hydrate, or about 60% saturation gas hydrate across this whole little mini basin. So we were 4 for 5 for drilling gas hydrates in that expedition, and they matched the pre-drill saturation. They were in discrete sand-prone facies at Green Canyon 955, Walker Ridge 313, and this was the first time that a specific seismic attribute associated with a pre-drill prediction was drilled in that manner. And that led us to confirm a model that deep water marine sands would have a wide, gas hydrate-filled sands would have a wide diagnostic signature in seismic data. And that would be larger and easier to interpret than the diagnostic range that's used for determining conventional oil and gas saturation. The implications on this diagram is there's a thin bed amplitude response for gas hydrates to saturation that's proportional to the amplitude and extends across the whole impedance spectrum. So that means that you can, that provides the basis for the development of several more effective techniques using seismic data. But think back to the triangle diagram that I showed you earlier. There's orders of magnitude more gas hydrate and fractures and undeformed muds. And the seismic tools that I just talked about, or concepts, they're not going to help us here. And these gas hydrates are going to be more or less invisible to us, and except that we might be able to roughly box them in where they might occur in a local systems model. So the main ways to, there are 3 ways to dissociate and produce gas hydrate. You can reduce the pressure, you can increase the temperature, or you can do it with chemical inhibitors. The main way is to depressurize them. And at first they thought that this would, the pore fillings, the cements would be cemented, and would make it very difficult to pump them. But it turns out that gas hydrates are really quite dynamic quite dynamic, and they don't really reach equilibrium. And so there's an irreducible water phase between the gas hydrate and the sediment grains. So in the first short-term marine production test in the Nankai Trough, they had a small electrical submersible pump, and they drew water immediately, and they began dissociating gas hydrate within a few hours. So depressurization was employed at 2 marine production tests in the Nankai Trough. in 2013, 2017, and there was also one in China in 2017. Back in Japan, the first one, they had 20,000 cubic meters per day, and they produced over a 6-day period. Again, this is a scientific test. The second scientific test, they had 10,000 cubic meters they produced over 24 days. So that was a setback, and it was a setback for, well, the normal reasons. You had things were more complex, reservoir heterogeneity, and they began drawing some water around they weren't expecting to produce. But both of those were from thin bed, sand-prone gas hydrate reservoirs at the top of the pyramid. So in China, they had the longest marine production test. And importantly, this was down on the pyramid. So this is down in the muds. And there were pore filling glass, clay-rich silts and silty clays, and they produced over 300,000 cubic meters of gas over 60 days with an average of 5,000 cubic meters per day. So the main challenges for producing gas hydrates are going to have some similarities with deep water oil and gas production, but with gas hydrates, you're going to have all of these issues. There's going to be low temperature, low pressure, low production rates, higher gas to water production, solids and fines. You could have subsidence, and not only just compaction of the reservoir, but also perhaps subsidence at the seabed. But on the other hand, the ultimate systems that could cost significantly less than the systems that are used for deep water oil and gas production now. So preparations are progressing for a long-term production test from gas hydrates on the north slope of Alaska that's aiming for production from about 6 months to a year of continuous production. And this is funded by the US Department of Energy and the government of Japan. And it has the potential to develop the operational methods, how you shut it in, how do you operate a well like this? And it can also demonstrate resource feasibility. So will gas hydrates contribute to the global energy supply? Well, much will depend on the local energy availability, the demand, infrastructure, and really important to be policy drivers. So methane hydrate is the cleanest of all the fossil fuels. The transition from coal and oil to natural gas and renewables could open a role for methane hydrate. For the present, methane hydrate resource development is being done with governmental R&D programs and investments. But it is possible that the conventional wisdom that we'll never get that out, just like it was at the beginning of this story for shale gas, well, that could be proven wrong. Thank you.
We can't hear you anymore, Dan.
That is the end. So we have open for questions, Ursula.
We have one question from our own Michael Campbell, who has wondered, with increasing marine temperatures, would warmer waters release more methane? Interesting question.
Yes, that would be true in the Arctic, certainly. And then, well, and could be, you know, there's certainly the, even on what they call it the feather edge of methane hydrate stability, there are seasonal changes. So it could change from 7 degrees at the seabed to 4 degrees at the seabed, et cetera.
Mm-hmm. Well, fantastic talk. Thanks so much, Dan. Appreciate it. And we're moving on to the heavy oil and bitumen talk by Ian Kirkland. Take it away, Ian. Thank you.
Thank you.
Okay, thanks, Ursula. So similar to Dan, we decided to concentrate on a topic within bitumen and heavy oil rather than review all of our committee activities. And what we it's very exciting what's going on in the U.S. Gulf Coast in terms of the dynamics of the market. And it's important to know about the PAD system of the U.S., the Petroleum Administration for Defense Districts. The Gulf Coast is PAD 3, and the EIA keeps fantastic statistics, which are very convenient. So in the Gulf Coast, there's a tremendous amount of refining capacity, about 10 million barrels per day, which is more than half of the U.S. refining capacity. And in the Gulf Coast, there's a tremendous amount of coking capacity, which is developed when taking advantage of the huge resources in Venezuela and Mexico, good pricing and long-term supply. So you can see in PAD 3 here, there's a tremendous amount of coking, and they can handle 2.4 million barrels a day of heavy crude. So the Gulf Coast is an important opportunity for heavy sour crude providers. But there's been dynamic changes in supply. Most of the U.S. heavy crude under production is in California and regionally isolated. So Venezuela, Mexico, Canada, Colombia, and some of the other smaller South American providers are all in play. They have similar characteristics of their crude, as you can see in this. They're heavy and slightly sour, from like 2 to 3.5 typically. So they're all competitive to be used in that refining market. And what has happened recently is that with the shale boom and all the light oil that was coming on in the US, the amount of oil that has been imported since this commencement of the shale boom has declined dramatically, the amount of oil that's been imported into PAD 3. But the percentage of heavy oil using Canada, Mexico, Venezuela, and the South American countries as a proxy, you can see that it has increased quite dramatically. The total from these heavy oil providers has declined also, but is kind of flattened out at about, there's a 1.7 barrel a day opportunity, 1.7 million barrel a day opportunity. And Venezuela has been a disaster for a long time, and with sanctions, they've dropped out of sight. They went to 0 barrels per day imported in May 2019. So that represents a substantial opportunity. You can see Mexico has been declining slowly, but still chugging along. Colombia has been pretty steady at about 200,000 barrels a day. And Canada is an important story. It has really increased in the last decade, less than a decade. Here you can see a closer zoom in of that previous chart, where you can see here's Venezuela dropping out of sight. Canada started taking off in around 2013 when the phase 3A of the Keystone Pipeline allowed them to get access to better access to the PAD 3 area. And you can see that it's kind of plateaued around 500,000 barrels a day is what Canada can get to pad 3. So now I'm going to kind of review the 3 key players, Venezuela, Mexico, and Canada, talk about some of the details about those areas and pluses and minuses of what's been going on there. So Venezuela, it has the largest reserves of extra heavy oil in the world, 1.2 trillion barrels in place, 310 billion barrels technically recoverable. But long-term mismanagement, lack of investment, corruption, and most recently sanctions have crushed production and processing capabilities. There's also been a lot of loss of intellectual capital in the industry over the years. The advantage they have is they have a huge resource and ease of transport, but more to be seen in the future whether they can come back or not. The field, the Orinoco heavy oil trend is here in Venezuela, south of Caracas, and with good access to port facilities. This gives an excellent picture of what's happened with their production. Their daily production has declined from almost 3.5 million barrels a day down to, they're flatlined at under 400,000 barrels a day currently. And you can see after US sanctions kicked in, it really has basically flatlined since that event. Mexico, their crude is the Maya crude, and it's a heavy oil. They have some serious challenges with a decline of their main reservoir, the Cantarell field area, and their heavy oil reservoirs are offshore and they're complicated. Their advantage is the ease of transport. So you can see the Cantarell field. It's in the southern Gulf of Mexico here, and the Cantarell field it's a group of fields, and the new field is a KMZ. It's another group of fields. It has come on, and it is supporting the heavy oil production. You can see what's happened with Cantarell. It's gone from 63% of their oil production in 2004 down to 10% in 2016. The reserves of these two field areas are about 2.7 billion barrels of oil remaining, and in 2019 they were producing about 1 million barrels a day between them. And these two field areas constitute 92% of Mexico's heavy oil production. So basically all of it. So they're quite vulnerable to keeping these fields going and trying to find additional fields. On to Canada. Canada's main crude is Western Canada Select. It's blended in Hardisty, Alberta, and Canada has the largest oil sands deposit in the world. It's both mineable and in situ, as well as heavy oil. And you can see the three oil sands areas here. The surface mining just covers a small part of the oil sands area, and it's north of Fort McMurray. There are heavy oil deposits down here south of the Cold Lake area in Alberta and Saskatchewan. And the total resource of the bitumen and heavy oil is 1.7 trillion barrels, and the remaining reserves are 167 billion barrels. The biggest challenge Canada faces is access to markets, and I'll be talking more about that in a minute. And this resource is extremely expensive to develop, so high oil prices are needed. New mines need 75 to 85 US a barrel, and in situ SAGD is about 60. There's been a lot of environmental pushback from various groups. The advantage to Canadian heavy oil is there's a huge resource, a stable business and political environment, and a strong technical strength and innovation culture. So this is the pipeline story in a nutshell. There have been various additions that have brought oil to Houston, and it's this leg to Cushing brought the capacity to almost 600,000 barrels a day. This is the Keystone XL, which is a very political hot potato, and it would add 510,000 barrels a day if it could be completed. The rail network, you can see that basically it's coming down the Mississippi Valley. Here are all the refineries in the Pad 3 area. That's an expensive way to ship oil. So this shows how exports of Pad 3 are really pretty small piece of the action. If you look at total Canadian exports to the US as reported by the EIA, it's up to a maximum of about 4+ million barrels a day. Gulf Coast has it peaked out in October 2018 at 646,000 barrels a day. The vast majority of the oil that Canada exports goes to the Midwest. And the crude by rail is a smaller component of that. The maximum monthly amount that has been shipped by rail was 240,000 barrels a day. In Pad 2, rail is really not necessary as they have excellent pipeline access. And you can see this is total Canadian heavy oil production, and you can see what happened as a result of the price crash. There was a substantial amount of shut in. It was rumored to be 1 million or more, but these numbers suggest it was more in the range of like 700,000 barrels a day.
Ian, you have about 30 seconds.
Okay. So yeah, so a big problem in Canada is the differential, the difference between Western Canada Select and West Texas Intermediate. And you can see at one point it got over $40, and that's when crude by rail kicks in, when the differential is higher. But when the differential is smaller, like now, the economics of shipping by rail are very small. And lastly, you can see we had this problem with the big differential, and the government of Alberta tried to cut supply. So their cap was this dashed line here, and this was the actual production. And here, most recently, is what has happened. So I'm not making any conclusions. Time will tell who benefits from this opportunity and who does not. There is a fantastic opportunity there, and I welcome any questions.
Thank you so much, Ian. Interesting summary and developments going on with the heavy oil. I have a quick question. At what price does heavy oil production become uneconomical?
It depends on, well, it looks like, well, SAGD expansions are economic at about $52 a barrel in Canada. I don't know what the economics are in Mexico and Venezuela. They have lower price points in those markets.
Okay.
That's a good question.
Yeah, thank you. Maybe not that economical right now.
No, that these big projects, they have to keep them going as much as they can during the tough times. Yeah.
Well, let's thanks again, Ian, and let's hear from Jack Passion what he has to say about developments in coal bed methane. Jack, please share your screen.
Okay, well, hello. It's a pleasure to be here this afternoon. I'd like to introduce my co-authors, Brian Cardot and Maria Mastallerge, and together we are the EMD Coal Bed Methane Committee. I'm going to give you a general overview of what's going on in coal bed methane right now. When you think of coal bed methane, it's a shallow, continuous, unconventional reservoir. Generally, the depths of production are less than a kilometer. There are some exceptions. Coal is a very unusual reservoir because it's a mesoporous polymer with very high gas storage. So because of that, gas is stored by adsorption in very small spaces. And in order to recover the gas, you have to lower the pore pressure. And that makes coal bed methane a hydrodynamic gas play. And you have to really approach it with a unique mindset compared to most other oil and gas reservoirs. When you look at global coal bed methane resources, there's about 8,000 TCF out there, so it's a huge resource. There's a very mature industry in the US and Canada, and production is declining. But if we look globally, the bulk of the resources not only in North America, but also Asia and Australia, and especially China and Australia are expanding production considerably. The US is the historic leader, and if you look at the top curve here, that's historic US production, and around 2008 it did start declining, and that's a combination of two things. That has to do with increased maturity of the coal bed methane reservoirs and also increased competition from shale. So it's a harder market to get into, and you don't necessarily want to drill too many wells at the current price point. Internationally, we can see the rest of the world compared with the US, and China and Australia are undergoing the most significant expansions, and Australia, as shown here, is on path to catch the US in 2016, and they certainly have done that since then. When we think of coal bed methane technology, there are a lot of ways to drill and complete a coal bed methane well. The most common is a vertical well, and it's a little different from most oil and gas wells, in which water is produced through tubing, gas is produced through the annulus of the well. And since the 1980s, many of these wells have been drilled vertically and stimulated in multiple stages. Something that really opened up a lot of the low permeability coal seams is precision horizontal drilling. In coal, operators can stay in a coal seam as thin as 1 meter and drill for 1.5 miles or more than that. So it has provided a lot of access to low permeability coal, and that's been a huge help in places like the Appalachian Basin. China relies on it strongly, and most basins now have some horizontal wells. Also, I'd like to point out there are a lot of pinnate wells, which are really complex multilateral wells almost like a leaf pattern leading to a central production well. When we think of coal, we think of a solid black rock, but in reality, it's a macromolecular net. It's a big polymer with a lot of spaces in it, essentially in between an aromatic framework, essentially a network of benzene rings. And the little red dots are this is a model of adsorbed CO2 in coal. And so all these little spaces is where coal clings to the coal structure. And the way this works is that because the attractive forces of the coal surfaces, you can store gas at near liquid density at much lower pressure and temperature than would be predicted by ideal gas law. So coal storage follows the adsorption isotherm. And if we look at the shape of the isotherm, all the action is at relatively low pressure. And that's a lot of the reason why coal produces at very shallow depth. And generally at around 1500 PSI or less, a common coal bed methane reservoir will contain about 7 times as much gas per unit volume as a sandstone reservoir with 10 to 20% porosity. Well, the gas is absorbed in the coal matrix, but it diffuses through the matrix to natural fractures. In coal, there's a very closely spaced fracture network called the cleat system. And you can see some nice examples here, a bedding plane example and a vertical outcrop example. And because there can be so much gas stored in coal, even a 0.3 meter thick coal seam is reservoir in many basins. And in places like the Powder River Basin, then a 100 meter coal seam is the reservoir. So there's a lot of variability here. So, and ultimately the cleat system is important because that's our principal source of permeability that facilitates the commercial flow of gas and water toward a coal bed methane well. Now, permeability is a real tricky thing in coal. We generally look at permeability of a sandstone and that's the value. But the cleat, it follows the cubic law for aperture in cleats, and it's highly stress sensitive in coal. And that's part of the reason why most production is shallower than a kilometer. And permeability typically decreases exponentially with depth, with near surface coals having permeability on the order of hundreds or even Darcy class permeability. By the time you hit 800 meters in many basins, you're down around a millidarcy. There are some exceptions, like the San Juan Basin at about a kilometer. There's still hundreds of millidarcies of permeability. So it varies basin to basin. But permeability is also a time transient reservoir property. And you can think of coal as a big molecular sponge that shrinks when you pull gas out of it. So in order to history match coal bed methane production, permeability typically has to increase by more than an order of magnitude. Generally 15x increase in permeability over the life of a coal bed methane well is common. That's because the matrix shrinks and the cleats become wider, facilitating more flow. Cleat spacing is really related to stress and thermal history of a basin. And generally, your more thermally mature coals will have closer cleat spacing. And here's a map of the Black Warrior Basin in Alabama. And generally, coals that haven't entered the thermogenic gas window have decimeter scale cleat spacing. They go down to a centimeter when you get to the thermogenic gas window. And then the metallurgical coals shown in the yellow and orange here, millimeter cleat spacing is common. If you go into one of the deep underground coal mines, you see coal will come off in millimeter sheets. It's so intensely cleated. So globally, there's production from coal of subbituminous to anthracite rank. Thermogenic gas is generated at high volatile A or bituminous or higher rank. That's a vitrinite reflectance of 0.8% or higher. Late stage biogenic gas generated by microbes related to meteoric recharge at the margins of sedimentary basins. This often really charges the coal and makes it an economic resource really gets us up to very high gas saturations. And mechanical properties of coal change with rank, and so does the absorption capacity. The more thermally mature the coal, the higher the absorption capacity, the more gas it can hold. Stratigraphy, sedimentation, structure, and tectonics are fundamental considerations when exploring and developing coal bed methane. On the left is a cross section through the San Juan Basin showing the pictured cliff sandstone in this area, which is a strand plane barrier system, and then the thick San Juan coals that are the Fruitland Formation that actually have produced about 85% of the coal bed methane in the United States, and then kind of formed in a back barrier, backside of the strand plane setting. Structure is really important. Faults will cut your reservoir and drain and limit your drainage area. Here's a structure map of the frying pan anticline showing estimated ultimate recovery of vertical wells, and found that because of lower stress in the shallower coals near the crest of the anticline, they had higher gas recoveries. And on the flanks is an area where there's a lot of drilling of pinnate horizontal wells to recover that gas. And that's a lot of the industry in the Appalachian Basin at this point. Together, the stratigraphy and structure really put together the plumbing system. If we look at the big picture of most coal bed methane plays, they are hydrodynamic plays. In the upper left is a model of really applies to Western Canada and generally low dipping areas where there is very limited recharge. Western Canada gets a boost because it's been under kilometers of glacial ice that have melted off, and the uplift has opened up the cleats. And these tend to be very water poor reservoirs, very low pressure reservoirs that produce very little water or no water with the gas in some cases. And if you have no water handling, that can really help your business. Normal pressure and under pressure, that's very typical of the Paleozoic coal basins. In these basins, if there's a structurally upturned basin margin, fresh water enters the basin and will support normal reservoir pressure. That dissipates into the basin and interior. And again, the entry of microbes with freshwater plumes is generally how we generate the late stage biogenic gases. And Western coal basins, we tend to see a lot of overpressure. There can be artesian overpressure related to elevated areas along the basin margins. And also there are zones of active hydrocarbon generation in the interior of the basins. And if there's our permeability barriers in the system, then you can generate quite a bit of overpressure. And that is part of what makes the San Juan Basin a world-class coal bed methane play. So to wrap up, coal's an absorption-dominated reservoir, requires lowering of pore pressure below the saturation point for commercial gas production. Lack of conventional trapping mechanisms really necessitates a very different approach to exploration and development, and understanding basin hydrodynamics and geothermics is essential. And there are a lot of technologies out there, and multi-stage hydraulic fracturing and precision directional drilling unlocked a lot of these resources, much in the same way that more recently they have unlocked shale resources. So thank you very much for your time. And if there's time for questions, I'll be happy to take them.
Thank you so much, Jack. Excellent review of the coal bed methane, excellent summary and explanations. I learned a lot. I have one quick question that's by Jeremy Platt. He had heard that the old San Juan Basin was the US greatest coal bed methane source or major source of methane leakage. Is that true?
I know there are a lot of natural gas seeps, especially on the hogback monocline. And there's probably some leakage from wells, but generally there have been natural seeps, certainly.
Mm-hmm. Yeah, okay, so nothing.
I don't think of it as production related.
Right. There's one more question by Dan McConnell. Is there a role for cores at in situ pressure for lab studies for coal bed methane? So for
Very
example,
much
in
so.
gas hydrates, we call them pressure cores.
Yeah, because the that's one of the real keys is the ability to recover coal and keep it intact at reservoir conditions. And most of the research that's going on right now is really in the sorption space and also looking at the pore systems in the coal to understand where the gas really is and how it moves. So there's a lot of room for that in coal.
Yeah, that would be interesting. Well, thank you so much, Jack. I really appreciate you coming and giving an excellent talk. And let's give it up for Jeremy Platt. Jeremy, if you would like to share your screen and talk to us about the changing US energy landscape. Welcome, Jeremy.
Let me see if I can get out of my share here. There we go.
Jeremy, you have to unmute. Jeremy, please unmute your microphone. Jeremy, unmute your microphone. Yeah.
Okay, my Zoom went away.
You're good. You're good. You're on. You're talking. Just go over your slides. Perfect. We see your slides. Everything.
I'm glad to see it. Great. Okay. Well, I really appreciate the chance to share information with you in this virtual format. I've had a chance to listen to some of the talks already, and it's wonderful to be able to jump around. And it's also great to listen to these nuggets from people with so much experience in our own committees. So I very much appreciate this opportunity. My co-author was busy giving a talk at the University of Houston yesterday. He's not being able to make it and join me live today, but his ideas did influence what I'm sharing. We recall we all started out trying to introduce what our committees were going to be, and eventually it all became condensed into this 10-minute story about highlights. I will say that we steered in very different directions by March this year after the Saudi oil price collapse and then the stock market price collapse and the demand collapse and so on. So all of that was incorporated in excoriating detail in our report that was issued in June. So now I'm just going to hit a few highlights of things that are sort of on our minds at present. The committee, with just a couple of slides on its background, it started in 1998, sort of kicked it off with a bylaw change, and it went back to the roots of the EMD itself, which was trying to provide a home for deal with many of the issues related to economics. When we started out in '99, we had a symposium on gas and electric power because that was beginning to look like maybe the growth market for natural gas, which turned on its head the idea that electricity and gas were always in competition with one another, which they seem to be at end use and colored attitudes for decades. We did a fracking or contributed to a fracking technology workshop in 2012 in Golden, and we were planning to go out to see the Mont Belvieu natural gas liquids hub just east of, like 35 miles from downtown Houston this year. But we got called off by the pandemic. But maybe next time we get back to Houston, we'll be able to take up Enterprise Products' offer to visit their properties. We're just looking for a new normal, a better normal. Our job is, we sort of introduced in all these committees, is to provide some digestion and reflection of current events and what it may mean. And it's always like swallowing a whale. I mean, it's one thing to pick off something very, very specialized, but you pick up something like that this topic is, where do you stop it? You know, it just is terrible. I think some of the themes of what we've been digesting and reflecting on over the years has been to follow this roller coaster. Supply shocks is a big theme. And it's a long way from the famine of the 70s, which we've written about. And it's important to understand a little bit how different things have changed. We had a demand shock this year, amazing, but because it went down, but we also had an up shock in the sense that we've had highest levels of use in gas and power generation and highest LNG export and things like that. So we're really bouncing around between extremes in these markets, and we try to cover them with some reflection and some data that people can digest relatively quickly when you're doing something else with your careers. There are winners and losers, and probably the biggest winner we've found, of course, is the consumer. And I had a career related to buying fuel for electric power companies. You know, never have so few people done so much to affect the purchasing side of the markets, except for maybe Cheniere nowadays, than the electric utilities buying massive amounts of fuel. And so that gave me a consumer perspective. And in 2016, we looked back and found out how much money did consumers save globally because of fracking. We drove down the oil price. It wasn't Saudis that drove down the oil price. It was fracking that drove down that oil price. And we found out something like $750 billion were saved in that 1 year of 2015 alone. And some of it's hard to document. So maybe half of that was in the US, mostly related to oil. And the rest is in the world, mostly related to oil and some degree to LNG. But we also translated that all the way through the electric supply side, because natural gas and its cheapness drove down the price of electricity. So there's a whole story there that we got into in some depth. I mentioned history. We have really broken norms in this industry at several different times. For example, why would you drill when the price is low? Well, that's what we did in gas. That was the first time we did crazy things like we did in the Permian. Now is we drilled for gas because we were trying to find positions into new plays held by production and that sort of thing. So there's a lot of cases where the normal cycles of mineral economics have been totally broken by an industry following different financial models, throwing money at a situation independent of the price signals in the market. A lot of things we've dealt with. I would recommend, like everyone else has recommended here, go to the resources you have at your fingertips. And this is just an example of a screenshot of pulling out what you get when you go to AAPG Energy Minerals Division and migrate to this obscure place for seeing what's listed. And these reports go back, I think, to about 2011 or 12 or something like that. It's available to you to get into more depth. Come this spring, we were having a leadership meeting, and we do this almost monthly. And I prepared something for us to discuss on the phone. We decided maybe it was interesting enough to throw into the May Explorer. And this is looking at prices over time through March at this point. No point in really updating it since then, but the point is, back in the day when we did have all this gas coming on line, that was the price schedule up top. When the price collapsed, we had something else to do with our money, which is to go for oil. Now, what I say, there's really no life preservers, and everyone's underwater. I hate to overdo that metaphor, but that's sort of the background. We're really in a cognitive dissonance because we are hitting high marks in so many areas as an industry. Never imagined that the US could do these things. I will not use the word dominance, but we had crude peaks from September through March at over 12 million barrels a day. The gas production peaked at 92 BCF a day in 2019. It's remarkable. I think we said something like 76% of that production was from shales. I mean, just who knew that? Or could have imagined that could have happened. I never could, and we tried to forecast that for a while. Record gas for power generation, we've heard about 45% of generation, highest ever levels was achieved in July, and that turns out to be almost coincidentally 47 BCF a day. We had the lowest level of oil and oil product imports. 20 of 37 weeks through the middle of September were net negative for this country, which is this is the first year we've done anything like that in history, maybe a few weeks the year before. Record reserves being found, record in oil and gas. They're reported maybe in November or something, they come out the following year. Whoa, God, it's knocked over my desk. But we're all still on the money here. Now I want to talk about the bad side of things. For some reason, I got stuff in my computer. Zenith, the nadir, the other flip side of the coin. I show what we all know on the right, the 72% drop in jet fuel use and the 36% drop in gasoline use, and sort of where that's been going, and is still far from where it needs to be to have a healthy market. Everyone talks about that. I thought I'd show that as my visual, but there are other things we don't always focus on. For example, there's been unbelievable record of low refinery utilization post-pandemic. 18 weeks below 80%, many weeks, even kissed maybe 69% for a week or something like that. Record low rig counts, record amounts of gas in storage. We're headed for another record, I think, this fall. Prices are, as I mentioned, are in the toilet. Financial distress is translated immediately from bad to worse, which happened to be, we kind of dissected that in our report, and we demarcated a period in the last few years when it was bad. It was bad when it went from $4 to $3. It was bad when gas went from $3 to $2. What is it when it goes below $2, which is also done with some record months this summer? LNG has been out of the money most of the time this summer. Record low prices in Asia as well as Rotterdam. So it's just been remarkable how bad things are now. But the seeds of being bad were well understood well in advance of this. They started turning bad by about 2017 when investors got fed up. So on top of the market fundamentals, which I'm mentioning, where are we going? Let's ask a futurist. By the way, how's my time? I dropped my watch. Could you give me an idea, Ursula? I don't know, maybe you can't. Okay.
Yes, you're good. You have about 5 more minutes.
Yeah. Okay. So one of the questions we might have is just, things are bad, but they're also terribly uncertain. So why not ask a futurist, but not just any futurist? Let's ask a futurist who teased on the topic of futurism at Shell Oil. So that would be initially Pierre Wack, who's the father of all this at Shell, but one of his disciples was a guy named Peter Schwartz, who had some training out at Stanford Research Institute's futurist and uncertainty scenario planning group under Jay Ogilvy. And it's interesting to hear about this. I've been following this type of planning and thinking and futurism for decades because the power industry was always wondering about how do you make big decisions under uncertainty, and this is a valid method. And one of the things that makes it valid is that Shell used it. But this guy said about the pandemic, it's been worse than the oil crisis of the 70s, the financial crisis of the 80s, the wars of the 90s, the financial crisis of 2008. I mean, he says it dwarfs them all because of its magnitude and ubiquity. What is it? We've heard over 2 billion people or more have been totally affected by this worldwide. The outcomes are not predetermined at all. And so that's one imperative. Where are we going with all this? The trends in environmental discourse I capture through one of my favorite tools, which is skimming through Google Trends. I typed out here fracking and climate change, and to see where they're going. I had a discussion with Ursula, was it Gasland that really kicked off fracking? Well, a lot else has kicked off besides Gasland. That's the red curve on the bottom. And it tended to subside a little bit, but it's still in the politics today. We hear about banning of fracking and the like. Climate's definitely on the radar, and we see many, many companies moving in the direction to change their policies. Out here in California, today was another bad day. We had 180 air quality index, one of the worst ones down in Palo Alto. But I'm showing here a map from September 9th, was when we had the margin skies that you might have seen on the news. Everything was, the wind was blowing out to sea, so you see the smoke moving on the left. I pulled something off of purple there, and you can see how bad the air was all up from Vancouver to Tijuana. I mean, it's just amazing. So that's not going to reduce the momentum of climate change. That's hanging on our heads. I'm just showing an example here as we turn to this, the financial implication. Apple going one way, the Dow is kind of flat. Exxon going down worse, and the oil field services index worse than that, as we know. And there's no end in sight of anyone wanting to go in this direction. There's a sea change in investment that we are trying to track in this committee. Environmental, social, and governance issues is not a fringe movement. It's been really deep in the Shell board boardroom, BP, Total, we're going to hear more and more about it. We had speakers from Shell yesterday, really great talks on AAPG. You can climb right in and hear what they're saying about the sky scenario and where things could be going. The oil and gas sector is on the ropes. It's not a growth industry. And the question about value, the Shell CEO was asked, can sacred payouts to shareholders be maintained? And his answer, I think not. What we're going through now is changing paradigms, is what he said. My friend, my colleague, Dieter Beeke put down what he called the 4 Ds of transformation: decarbonization, disruption, digitalization, and decentralization. AAPG is actually quite active in many, many of those areas. But it sounds like kind of flaky stuff at first until you kind of climb into it. And you still wonder, how flaky is it? Well, it's not that flaky. Turns out SPE has been into this for a long time. It doesn't all sound as flaky as Gaia. This is my last slide. Look over the fence. See what SPE is doing, the Journal of Petroleum Technology. There's much to learn from, and I think we're going to be shifting our directions towards that. We need to expand our view of what is technology. It's not just lateral feet and more proppant. One thing you're trying to do and stay on top of is articulating a map of what this situation really is. One of those is a great talk that Dieter gave yesterday at the University of Houston, and he'll be sharing elements of that probably on our mid-year report. We need to combine energies and knowledge, and we think we contribute to proposing a symposium maybe at the annual meeting next year on what does it mean to dismantle the fracking revolution? Is it going to happen? Where's the investment going? Are we going to see gas and oil competition? Is hydrogen really going to be lift our boats? How many boats can hydrogen really lift? Sometimes people get really excited about an element of this, but it's not the old industry. So this is sort of what we're trying to ride, is this very bucking bronco of a series of markets and changes in our industry, and summarize some of that for all of you. I'm done. Thank you.
That was excellent, Jeremy. Thank you so much. What an amazing review of the ups and downs and of the energy markets, oil prices, and so on. We have one question for you.
Yeah.
If you don't mind. Jack was asking, how do you see things recovering as we approach a new normal, as we move through and hopefully past the pandemic?
I think we're in for some permanent changes, particularly on things like lifestyle. So we don't see the mark. I think there's some arguments that, is the peak oil ahead of us? I think to some degree maybe we've hit that peak. I think there's a growing consensus around that. But there's also a great knowledge, and Scott Tinker spoke about that 2 days ago, that much of the rest of the world really needs energy. And so gas has to play a major role in that transition. So I see things being a glide path, not and with greater intelligence on the part of our political parties. Maybe people will recognize that if there's more facts mixed into the puzzle, we'll see why we need a collection of resources to move forward without too much disruption. So I'm not that negative. I think it'll be a glide path, not falling off a cliff.
Yeah, that's very interesting. And thanks a lot, Jeremy. I don't have another question.
Thank God. That was a tough one.
I really wanted to thank everybody for attending the meeting, and especially thank you to all of the committee chairs for doing really a lot of work, hard work for free, and posting all of their amazing research on the EMD website. So if you would like to become involved in any of the committees, please send any of the chairmen an email. You can also send me an email and I will hook you up. We are always looking for volunteers and people that provide their knowledge, and we know you're out there. If you're unemployed or if you're employed, it doesn't matter. I know you have a lot of knowledge in some of those amazing topics that EMD is offering. So thanks a lot to everyone, Justin, Jeremy, Ian, Dan, Mike, Jack, Lucy, and hope to see you next year in Denver with even more topics in real person. Thanks for the Freeman Company and AAPG for putting on this virtual meeting. It's been a big pleasure.
Thank you.